All right, guys, welcome back to part 2 of the SSS and SAS video notes. Now we're going to move on to a second congruence theorem, the SAS congruence theorem. And as you can see right here, we have these two triangles. And I'm just going to start marking this up. So we know that AB is congruent to DE by this figure. We also know that this angle here, angle B, is congruent to angle E. So it's congruent to angle E. And we also know that side BC is congruent to side EF. And if we can establish that, two sides and the included angle of one triangle is congruent to two sides and the included angle of another triangle, then those triangles must be congruent to one another. So we would say that triangle ABC is congruent to triangle DEF. Now I want to talk about this word included, okay? So included angle means the angle touches the two sides that we're talking about. So like if we were talking about side AB and side BC, the included angle between them is angle B. If we were talking about side AB and side AC, the included angle would be angle A in that case, all right? So when we do SAS, we have to be very conscious that the two sides that are congruent on one triangle to another triangle, the angle between them must be congruent to the other triangle, all right? So let's take a look here at our first SAS proof. So we have that JM is congruent to NL. We also have that angle JMN, which I'm going to put a little arc on right here, is congruent to angle LNM. And then once again, if you take a look, these two triangles share a common side, which is side MN. So we know by the reflexive property that MN must be congruent to itself. All right, so let's work on this proof. The first two are given. So that's a side, an angle. The next thing we say is that MN is congruent to itself. That's the reflexive property.
Sorry, I don't know that.
And MN is a side, so we have SAS. And that's going to fill in our reasons for why the triangles are congruent. SAS. All right, let's move along. So here we have that AB is congruent to BC. And we also see that BD, so side BD bisects angle ABC. So let me highlight it for you. Angle ABC is right here. BD is a bisector of it. And remember, an angle bisector cuts an angle into two congruent angles. So that must mean that those two angles are congruent. And are the sides of the two, do the two triangles share a side? They absolutely do. So we know reflexive property is going to play a role in here. All right. So let's fill in our proof. The first two are given. The third one is because of the bisector. So angle ABD is congruent to angle CBD by the definition of an angle bisector. Anytime a problem gives you bisects or midpoint or anything like that, you need to use that as a reason in your proof. So we have side, we have an angle here, and then we have a side here. BD is congruent to itself. That's reflexive property. So what's the theorem that we can use? The theorem we can use is SAS. All right. Let's take a look here at number 6. It says V is the midpoint of WZ. Okay, well, here's WZ. So that must mean that WV is congruent to VZ. Oh, it's also the midpoint of XY, so that's perfect. All right, and you should already have in your head that you're probably going to want the angle that is between those two sides congruent. And if you take a look, these are kissing triangles. And we know that kissing triangles, they have vertical angles. Vertical angles are always congruent. So there you go. Bam. All right. Given why is WV congruent to VZ? It's the definition of a midpoint. Why can we say that angle WVX is congruent to angle YVZ? Why did we say those angles were congruent? Because they're vertical angles. Let's be very conscious and let's be very correct if it's vertical angles or vertical angles theorem. I'm going to go back up to my reference sheet up here. Okay, so it's totally okay if we just write vertical angles. That's totally okay. So that's angles. And then we also know XV is congruent to VY. That's the definition of a midpoint. Remember, when we were marking up our triangle earlier, we used midpoint. I can't circle these things. So that's a side, that's an angle, that's a side. So the theorem must be SAS. All right. Finally, number 7. HI is congruent to GJ. I hate when they use those two letters together. We also know that HI is parallel to GJ. Okay, so here we go with these parallel lines again. We see parallel lines. We see this line that kind of connects those top two. What's that called? HJ is called the transversal. So what do we know? We must know that this angle and this angle are congruent because they are alternate interior. Now, don't get it confused. Let me show you in red so that way you know not to do this. It's not this angle and this angle, okay? Those angles are not congruent because GH is not parallel to IJ, all right? Those sides are not parallel. It's HI that's parallel to GJ. So the angle that it touches those parallel sides, those must be the angles that we talk about. All right. And then finally, we know HJ is congruent to itself. That's reflexive property. Let's set this off. So we know that this is given. We know this is given. And we said that the angle GJH is congruent to angle IHJ because they're alternate interior angles. So that's a side, that's an angle. The side HJ is congruent to itself. That's reflexive property. And there we go. That's SAS for you. All right. Come in with questions on Monday, or maybe watch some other YouTube videos on this. But that is the basics of the SSS and the SAS theorem.